This is the Math Map Book Club, where ordinary parents encourage one another to develop an extraordinary appreciation of math. We love what we know and struggle over the unfamiliar. Through weekly conversation and exploration among friends, we can begin to enjoy ideas that seem difficult. Join our book club as we discover how math helps us to know God and to make Him known. Hi, I'm Lee Bortons, and it's Wednesday, March 13th, 2024. Welcome to the Math Map Book Club, where Christy Gilpin and I discuss right now 2 lessons each week from our soon-to-be-released math curriculum for families with students in classical conversations communities. In case I forget, happy St. Patrick's Day and happy Easter, and April 1st is my birthday, so happy birthday, Lee. It's an exciting week coming up for me at the end of the month here. So thank you all for joining us, and I don't know that you appreciate how happy Kirsty and I are that you are here each week. We love doing this, and we're so happy that people ask us questions and that we actually can make the unfamiliar familiar. So Kirsty, what have we got this week?
We are looking at lessons 19 and 20 this week. So we are going to be in 3D. So looking at our math map, we're still emphasizing the naturals. So we are still working through the naturals. That's what everybody has access to that is in CC Connected. So if you are a CC family, you have access to CC Connected and you have access to the naturals. So that's why we're using that. If you are not in CC, you probably don't know what you're missing. And I would encourage you to see what we're doing here and just know that there's so much more than this. So we are in 3D. Last week we wrapped up 2D, and this week we're going to talk about open shapes and solid shapes in 3D. And as always, we'll pause for a moment in case there are some questions that need to be asked before we jump in. Does anybody have some lingering questions?
I have one that you may want to save until later, Kirsty, but I noticed in the 2 booklets for this week, unless I missed it, I didn't find any instructions to read or say things out loud like we've had before. So I didn't know if that was on purpose or not.
That's on purpose. We needed the space, and we figured the parents either had developed the pattern by that time or not.
Got it. Thanks.
Thank you for putting it out. Your all's notes. I mean, we went over from this morning what you guys send us. It's really great to have you helping.
All right. Anything else? All right, well, let's go ahead and jump into our lesson pages. And looking at page 1 of lesson 19, I'm going to go ahead and give you a minute to talk about what is familiar and what is unfamiliar on this page.
Well, X and Y is familiar at this point, and I know when we got to this page with my son, that Z really freaked him out.
Can you tell me why, Jana?
Well, for one, he was used to the Y being, the vertical. And yeah, and then just adding that extra letter, like I think he was just finally sort of getting this whole rectangular coordinate thing down. And this just added a whole new dimension. Sorry, that was a terrible pun.
No.
But,
you know what? Something you can do with all your children is get an empty tissue box and draw an XYZ with a Sharpie, and then there you go, and then spin it around to show them it doesn't matter. But we do throughout the curriculum keep XY always positive XY always in the same alignment,
okay.
No matter how we spin it.
Yeah, we as humans tend to think a lot more in 2D because even when we think about our locations on the Earth, we sort of ignore the up and down part and think we like to think in 2D. We can master 2D in ways that we cannot master 3D because we're inside of it. So anybody else see some things that may be familiar or things that are not familiar?
the word simplify was familiar since we've been asked to do that on other pages.
Good.
Well,
How about-
I am familiar with pizza.
A little too familiar over here.
I really love the bottom progression. And I'm thinking because my challenge 8 kids, like I feel like they need, even though I know this is, the naturals, but I feel like that is something that you can put on the board to show them simply the comparison between the three. So I love that the comparison at the bottom.
Great. How about just the page in general? Does the general layout of familiar? Is that something that's restful? At this point in the year, we go, oh, well, there's 3 big sections of the page. We've become familiar with, all right. And so that even being familiar with that is something that we may start to discount because as things become really familiar, we start to sort of ignore it, right? But I just thought I'd point out that as we come into this, right, just the layout of the curriculum is a place where you can help your student feel familiar. You can say, well, how many parts of the page are there, right? Is that familiar that the page is broken up, right? So could we, if we feel overwhelmed page, could we hone in on just one of those pieces, right? And so it's okay to go back and say, what's familiar even in the layout that can give us rest, as well as as Babs pointed out, right? I might be really familiar with 1D, and so finding those things that are familiar to give us places to rest and then build on, is so just looking at our 2D and 3D rectangular coordinates. How was the plane divided? That 2D plane, how is that divided?
You mean like X, Y, up and down, left and right?
Like quadrants.
And squares into
Mm-hmm.
squares.
Good. So our axes, as Lee pointed out, we have our axes that give us a way of referencing the rest of the space. And then as Jill pointed out, we call those 4 big areas the quadrants, right? And so that's one way of sort of kind of like our continents, right? I can say, well, at least I know I'm here, and then I can narrow it down. So we've got our quadrants, and then I just want to point that out because here's an opportunity to go back and review, because I know some people have had questions about how to review in the curriculum or whether there is review, but working through the dimensions the way that we do, we're constantly going back and looking at these ideas. And so how was the plane divided? We just talked about axes. We talked about what that meant. We've talked about coordinates. We've talked about the quadrants. So we went back and reviewed those ideas now in order to pull that forward. And so if we think of our axes create 4 quadrants, how many axes do we have in 3D, do you think? 3. And so how many pieces does that break space into?
Hmm. Well, based on the cube shape, wouldn't it be 6?
Okay, so we might be tempted to think 6. So think about your plane, your quadrant, and you had 4 pieces, but now there can be a top and a bottom of those.
8.
And so there's going to be 8. Right. So we've got 8 different regions of space, and it's not on this page, but perhaps somebody who's looked at the charts or has worked through complex, do you remember what we call those?
Octants.
Octants. And how do you remember that it's octants?
There's 8.
Oct is 8.
Right.
Except for October.
Except for October. This is true. But the
Pre-Caesar,
octopus,
Caesar was 8.
Right.
He messed it up.
Good. So there's a wealth of conversation we had, and I also thought I'd point this out because I've had another conversation with a couple of other parents who sort of said, well, how do I take this naturals page and use it with my older student, right? And I reminded them that, right, first of all, it's becoming familiar with the layout of the curriculum. So going back and saying, look, remember what these bars do. We're becoming familiar with the layout of the curriculum. But then we can also use our learning, our skills of learning to compare and define, right? And look at that. So comparing 2D to 3D, or comparing octo, right? Octant to oct whatever. Right now we're maybe pulling in knowledge from memoria from other places to compare. So when we're looking at these pages, there's a lot we can pull out beyond just the grammar that we've put on the pages or becoming familiar with the curriculum. So that's first and foremost, we want people to be familiar with the curriculum. Second, starting to build that familiarity with the grammar of mathematics. But for those of you who have older students and maybe are looking for a little bit more, I just hope you feel really equipped and encouraged to just dive in and have those conversations.
So one thing people always ask about is the review, and I want to point out, Kirsty, then that bottom part where it has the XYZ numbers. For the little guys, all they're doing is reviewing addition and subtraction. It's just they're doing it in a form that eventually will become two equations with two unknowns.
Yep, and learning that you like terms, really. I mean, that's an introduction to, well, I can add these two together because they both have an X. I can add these two because they have a Y.
All right, looking at page 2, on the title of this page, Equations of Lines and Pages, and then our top bar is 2D and 3D polar coordinates. And so we sort of talked about my questions before, but let's go ahead and take a look at this page and what is familiar and unfamiliar on this page.
The Greek letter psi was unfamiliar to me.
Well, just polar coordinates in general are unfamiliar to us unless you use a compass a lot. But the thing is, they're very familiar to us when we're playing games with our kids, because you'll tell your children, like if you're throwing football, run 20 yards to the right. Well, that's a different way of giving a polar coordinate.
Yeah, so we're talking about a different type of coordinate system. Again, we can go back and look at what we might have remembered from 2D and comparing that to 3D. Then, as you pointed out, there's all these symbols, right? And as we add more symbols in, we may find that those symbols are familiar or unfamiliar. And that's a big part of math, right? That symbolic nature of math. And of course, to make things even more interesting is that when we look at that phi there, or some people say phi, we may recognize that as being the golden mean or the golden ratio, but here we're also using it as an angle, right? Which isn't us, just to make sure everybody knows that was not us as the math map that chose that, right? That is recognized standard about around the world by mathematicians. So understanding the context is important, right? Just kind of like punctuation in, right? Let's eat grandma or let's eat grandma, right? When we talk about how important it is to look at things in context and with correct punctuation, the same thing is true for math, knowing sometimes what the symbols mean to us.
That's why the glossary is so important, is because there are so many synonyms in the symbols in math. And obviously a child who's looking at this this new symbol to them, and yet they were made to memorize it in week 2 is something totally different. So that's why they struggle, and reading is a really important part of math first.
I have a question about the trace the octants part of this page.
Mm-hmm.
I'm trying to visualize a box and what corner of the box our perspective is from. Is that a good way to think about these?
Yes, and if you wait to it's mapped, so if you wait to page 6,
Yeah,
you'll see them all put together. So we had the kids just recognize there's X, Y, Z's and negatives and positives, and I know they don't understand.
right.
And then the next time they see it, it's put together, and they still won't understand, but maybe
Mhm.
mom will.
And then the other thing I was trying to do with that page as I was visualizing it is relate it back to like the top of the next page or the previous page where you had the X was coming down kind of slanted to the left and the Y was horizontal to the right and the Z was up. And those were positives, like a 3, 2, 4. But I don't see that one in trace the octants. So which one would that
We'll go
quadrant
back,
relate
Kirsty, so
to?
everyone knows what she's looking at.
Yeah.
Can you do that?
Sure. And then I'm going to show you something. So this is what Kathy's talking about is in that middle part there.
Yeah.
And now let's look here and think of these as at that center point is our center. So hopefully you can, so here, right, here's my 3 axes. And what we've done in the math map is made sure that even though we can turn these axes around any which way, the orientation is always going to be the same. So if I'm looking at this, right, pretend this is my XY. So for you, this is
Kirsty, it's
my,
probably pretty hard because you're coming in and out because of your screensaver behind you.
let me see if I can turn that
We're
off
losing shape.
easily.
But just while she does that, Kathy, quickly, the very first octant 1 matches the octant at the
Okay.
top page.
It's just spun. It's just
Yeah.
spun.
Mhm.
Okay.
Yeah.
That makes
So
sense.
here's, oh, let's see, can you, yeah, that's
Yeah, now
better.
I can see it.
Okay, so here's my XY, right? And we like to think of it this way because that's how we draw it on our paper.
Mhm.
Um, so here's my positive X, my negative X, my positive Y, my negative Y. And so whenever I spin this way, right? It's always going to be positive X and positive Y. I'm not going to reverse those. Well, when I talk
Gotcha.
about 3D, right? I'm going to lay this down now. So it really is like it would be on my paper. And I'm going to add my 3rd axis. And so my X, this is my positive X, this is my positive Y, right? And notice I could turn this here, and that's what you saw on page 1. My
Gotcha.
positive X, my positive Y. But I could turn it around, and now you might be looking at positive X, positive Y appearing to go back, right? And so I could turn that around. And so that's what's happening. Does that help, Kathy, a little bit?
Yeah, that's super. It's so hard to visualize 3D on a 2D page.
It really is.
Yeah. I like the Kleenex box idea.
Well, if you look at
When
the
we-
back of page 19, and once you get the curriculum, the game on 19 is to take a tissue box and use it to do all kinds of activities.
When we did this lesson in our Challenge A class, I used the whiteboard trivium tables and just kept it out on the table and brought skewers. And they could hold the skewer up off of the origin of X and Y so that now they have a Z. And so anytime anybody had a question, we just kept it out and we could pull it back and lift it and say, okay, let's compare what we see in front of us to what we're looking at on the page.
I like that. Did you ever put the skewer through the trivium table? Because that's
No,
that's the one thing
I
I'm
know.
thinking with the tissue box. If you're looking at this, let's say as the origin, you're really only ever looking at one octant, right? Whereas
Well,
the illustration you just did, Kirsty, with the ruler and the fork and whatever, you had your axis actually crossed in the center, and then it's hard to make another one that goes all the way through. But that's where my tissue box kind of breaks down a little bit.
You're right, Jana, that thinking of that, when we think of a corner of the tissue box, we are just looking at one of the octants. And so it still is really helpful. But yeah, when we want to see how all of those octants, it really, your body is going to be one of your best ways, right? So if you think about standing up and your arms, you could even do your arms this way or this way, right? Because now I can think I've got my body is sort of the Z axis and the origin. And then if I think about my shoulders being, maybe this is my origin. So now I can go, okay, well, here's my X axis, here's my Y axis. And now I can start thinking about, okay, above my shoulders, to my left, in front of me, I can picture that octant and so forth. So even just using your aesthetic learners to start talking about where each of those different octants are.
And you can always get Legos and draw on them too.
I mean, you could do it lots of ways. You could even have kids hold string across the middle of a room and lift, at shoulder height, and then talk about where you are. You can't, it's just one thing. You can't do it the whole day. You got to sit down or maybe put the string down and do other stuff, but it could introduce it.
Yeah, I like that. You could hang a string from the ceiling and then have kids do the X and Y. Oh, I like that a lot. I write that down.
This is a place where the concrete and the abstract, the more you can do both of those, they will begin to merge once they're adults. So all these bodily things you're talking about are very important for your high school students. As an adult, as a mother, you guys are all benefiting from this. And we forget our older kids need to do that too. And then meanwhile, they're doing calculations, and one day the two should be able to merge. And that's because that's how all of life is. You don't always know what a word means for a while until you've experienced it enough.
All right, let's look at page 3. And our title of our page is Intersections of Lines and Planes. And just a reminder that we don't always see our titling is designed to point us to where we're going. And so sometimes you may go, well, where does that show up on this page? But all of these activities that they're doing as 5 and 6 year olds are pointing them to what they're going to be doing in their upper challenge years. And so those bars are intended to give you a hint as to where you're going, even if it doesn't necessarily describe exactly what you're doing there. It's part of that mapping. Kind of like when you're getting on the subway, right? You might get on the Victoria line, right? Well, I'm not going to Victoria, but it's called the Victoria line because, right, maybe that's its end destination. And so even if I'm not actually going there now, that's the direction I'm headed in. So that's that idea of that mapping. So again, now we've looked at rectangular coordinates and we looked at polar coordinates. Now we're comparing the two. And so what is familiar on this page, or what's something that's unfamiliar and looks interesting to you on this page?
I was going to go back to the letter psi on our polar coordinates. I just had never thought about polar coordinates in 3 dimensions. So it's really interesting to think about, like Lee was saying, go out and to the right or out and to the left. And then, but with a globe, how far down am I coming?
Mm-hmm.
It's just a fun thought exercise.
Oh. I don't know where those yellow lines just came from.
Mm-hmm.
All right. Well, so let's talk about the number of coordinates, right? How many coordinates do we need for the rectangular system? To kind of go with what Alyssa was saying.
3.
3. So how many coordinates are we going to need in our spherical or polar system? We're going to need 3, right? And we are really familiar with those 2 angles, right? Because those 2 angles are our latitude and our longitude. So we're all really familiar with the 2 angles that we use in spherical coordinates. we usually just drop the R because we just think of the surface of the earth as being the same R wherever you are. Right? Unless we're going above or below the surface of the earth. So even though our R is really different, we're still just saying the surface is our constant. And so the two angles that we use, so Alyssa, that was a great way to talk about using that globe, because that's the two angles that we use, right? We measure our distance in the XY, and we measure that from our prime meridian. And so we measure that this way, and then we measure from our axis, right, up and down. So we have those three coordinates, and that may help students, right? If you think about latitude and longitude as being angles, that may help students to grasp what we're talking about there.
Yeah, and then the surface of the earth is not in one spot either. Like we often, I guess we use sea level would be kind of like the origin for that. But you can go up on a mountaintop, or you can go up in an airplane, or you can dig down, with a bore into the earth. And that's, so I like thinking of, I kept trying to think of the radius and theta as latitude and longitude, and then I had to try to get this other angle. So I really like using the radius as the elevation or altitude instead. That's good.
All right, let's take a look at page 4. And are again looking at continuing to look at these different types of coordinates and how we're building these coordinates in 3D. We're also going to take a look at 3D vectors. And so if we think about a vector, and we've defined these vectors in 0D, and it was just the null vector, but then we talked about 1D and how many coordinates could a vector, or did a vector have in 1D? 1, right? And how many coordinates did a vector need in 2D to be defined? 2. So how many vectors, how many coordinates are our vectors going to need to have in 3D?
17. No, 3.
So there's the beauty, Jana, you're correct. It is 3, but there is the beauty of working with vectors, is that once we start to understand how you work with vectors, I can work with those vectors in any dimension, because what dimension would have a 17 coordinate vector?
The 17th dimension, which we
The
cannot
17th.
think about, but we can still talk about it because of the patterns. Yeah,
Exactly. And so we could actually define lines, and we could find intersections of those lines. It would be a lot of computation, but we could do it right in 17D, because the way the vectors work is consistent, right? And so that's really the joy of vectors that I have discovered over the last 7 years. And Babs, because I know you love the little ant, does it matter which of our coordinate vectors he walks first? Does it matter if he goes X, then Y, then Z, or Z, then X, then Y? Does it matter? Would it matter the order?
I don't think so.
No, he's always gonna get to the same place, right? As long as we keep the magnitude and direction the same, right, consistent. We can't swap them and think they're going in a different direction. But yeah, so we see him walking along, and he could have gone in any of those. If he was just going to walk the coordinates, he could have done any of those to get to that same point there. And that's because what law lets us change the order of our addition?
commutative.
Commutative, right? So there we go. So here's one more way we can go back and practice those things that we learned in 1D, or our memory work from foundation, and we bring it in here. And throughout the year, we're continually going back and saying, okay, well, why does it not matter whether I go XYZ or ZYX to get to my point? Because of the commutative law, right? That here's an example of applying that. Right. Anybody have any last minute things they'd like to say about lesson 19 and open shapes?
I want to point out in the middle of 4, because we had another question about this, and I don't know if this will help either. But for those that are concerned, keep working on that XYZ and how it rotates around. Here we're showing it a different way. We should try to show a variety of ways that these axes can move around. And then once you get into, once we're kind of past doing 3D manipulations, and move on to rate problems and things, you'll get back to that more familiar XY plane. And then once you get back into complex numbers at the end there, you'll get back into Z. So we've tried to have it so that, that's part of the review, is seeing it different ways at different times. And it is hard at first to get it straight. Keep asking, and you'll get it right, and then no one will ask you for 2 months and you'll forget. And so ask again, how it works.
Yeah, even in 2D, we usually say length and width.
Mm-hmm.
And my son was like, why isn't it length and height? Because it looks like height on a piece of paper.
But in
it
3D,
can be either, as long as you're just using 2 of the dimensions, right?
It can be. And then it's just up and Z go together. And when Z is up, then it does become length and width more often, but not always, because you can spin everything.
Yeah.
Great. Just a reminder of our release schedule, what is coming for digital versions, what is coming for the print versions. Are there any questions about the curriculum before we jump into lesson 20?
I guess I want to say one more thing you made me think about. Because I've been told like some of these problems are too easy and they've seen it before. And I'm like, okay, just because your eyeballs were on it doesn't mean you saw it. And when something's unfamiliar, it has to be, your eyeballs have to go a lot of times before all of a sudden it registers what the person's teaching you is trying to get you to see. And so just be patient with yourself and your kids on these things that are unfamiliar. And this is again why we see the same kind of simplistic problems for 8, 9 years in a row, very similar to each other, before we start putting the computations in.
All right, well, let's go ahead and look at lesson 20. And so when we were looking at open shapes, we didn't really talk about what it meant to be open, versus this week, lesson 20 is closed shapes. So let's pause before we talk about the lesson page and just for a minute talk about what would be an open shape in 3D and be a closed shape in 3D. Is there anybody who wants to jump in and share what they think?
I was thinking of curved surfaces, almost like a bowl, and thinking of how it would, like a 3-dimensional parabola, like a filled in parabola would have that open shape where it just keeps going into space.
Mm-hmm.
That's the first thing that I thought.
What about like a watering trough for a horse?
Yep.
Basically, you could take anything on page 1, any of those 3-dimensional solids, and if you just knock off a section of it, it's now open.
So a trash can.
Mm-hmm.
The shape that the ant made when it was taking those different vectors be like a open shape.
Be like taking the lid off a box.
Good. Now, of course, right, when we think about things in 3D, anything that's actually solid that we can see is actually going to be closed because it has some dimension, right, in all of those dimensions. But they give us a good image of what that open shape would be, that that it is having some, right, that it's not closed. So that's like one of those weird things when we think about, like, am I talking about just the trash can without the lid on, or am I talking about actually the pieces that make it up, because they would be closed, but then the sort of the system could be open, which is probably going farther than I needed to go. But
that's okay. No, and of course, because they're going to see all these terms. Like, I'm thinking about, I struggled a lot with this and had to come to Kirsty very, very often. And I'm so glad she was a geometry teacher for so long, because I was really struggling with open and closed versus inclusive and exclusive, versus bounded and unbounded. And they're all math terms that superficially look the same because we draw in 3D space, which is not very accurate. And yet they mean totally different things. So what your eyeball's even seeing, your brain may not know which abstract idea to attach to it, even though you might be seeing it appropriately. So I just want people to, continue to be encouraged by struggling.
I think this is one of those concepts that, again, goes beyond being good at calculations or being experienced with calculations, but understanding what it is you're actually looking at and being able to describe that or ask limiting questions if you need to. I'm sure that in professional careers, these are questions you need to know. You might not need to know it to answer it on your, the thing you're drawing on a test somewhere, but you do need to know. If you're working for NASA, I'm sure they want to know open or closed.
Right. So let's take a look here at lesson 20, and we are talking about regular polyhedra. And I'm going to jump in with a question and ask who remembers or recalls what made a polygon regular.
It's when all the sides were the same length and the angles were all this equal.
Excellent. So all congruent angles and all congruent sides. And notice what we're doing, right? In lesson 19, now we're doing it in lesson 20. We're continually going back and saying, okay, what patterns do we notice, right? So what was true in 2D, how does that help us to see something that's true in 3D? So taking that congruent angles and congruent sides, what's true about a regular polyhedron?
I would assume that would mean that they have the same length sides, and congruent angles in all three dimensions.
Good. So you're right. All of my edges, we're going to actually call what were the sides, right? Those segments are going to become edges, and the sides that we may think of are called faces. But all of those faces are going to be congruent, which means that all of those edges are going to be congruent, and all of the vertices where those sides meet are all going to be the same, right? And so we're going to have these polyhedral angles that would be the same. And so we were able to take what we knew from 2D and look at it in 3D. Does anybody not, right? It is on this page. If you look closely enough, how many regular polyhedra are there and what are they named?
You're muted, Alyssa, if you were talking.
I'm sorry. I was like, it seems like there would be an unlimited number of polyhedra. But I didn't hear the first part of your question. How many there were on this page? And then I saw the 30-sided and I was trying to figure out what it meant. So I said it out loud. Thank you.
Oh, that's wrong.
So it feels as though there should be an unlimited number, but there actually are not, right? Because in order for my sides to all be congruent, we're actually going to add one little detail there, that they are congruent regular polygons themselves. If you look at the bottom of the page, there are 5. There are only 5 regular polyhedra. Right? So we had an infinite number of regular polygons, but there are only 5 regular polyhedra, and we call them collectively the Platonic solids.
There's an error there I just saw if you're asking. Both the E's aren't 30.
So those are our Platonic solids, and those are the only regular polyhedra that we have. anything else on this page that stands out as something that is interesting to you?
I think identifying the vocabulary of faces, vertices, and edges would be helpful for, well, I guess depending on what age you're talking to, but I think that's something that kids need to figure out.
And that's where
we would speak all the time, like describing our house. It's on the, on the west side of the house. When really we might mean it's on the west face of the house, if it's actually on the wall itself. So that would be a place to start using the words properly.
And that's also where the tissue box is really helpful too, because now I can actually hold my tissue box and I can say, this is a face, right? But this is an edge and this is my vertex. And then you can also go back and review your dimensions, right? Because altogether, my solid has 3 dimensions, but my faces have 2, my edges have 1, and my vertex is 0 dimensional, right? So I can review that. And actually, Lee, they do both have 30 edges. I wanted to look that up before I said that. They, interestingly enough, but they have different numbers of faces and vertices.
I don't believe
So-
you. I'm gonna go get some and count on myself.
You can. I promise you it's true.
Well, the cube has 12 edges, and then that octahedron, it says, has 12. So that's a similar thing.
Yeah, 4 and 3 make 12 two different ways. But 12 and 20 don't make 30 two different ways. I'm not believing it. But see, that's we need to model for your kids too. The answer key might be wrong. It's okay. Go find out.
I counted them. I came up with 30 on both.
Okay.
I counted them this morning because I didn't believe it either.
Yeah. Okay. Well, good. I don't have to change it. I'm still gonna go find out though.
Just to follow up with that point, the dodecahedron, these are really hard words, but that is a 12-sided figure. Is that right?
Yes, that is.
And then the
Do- Icosahedron,
that's
So-
a 20.
that is 20. So the tetrahedron is 4 sides. Hexahedron, which we commonly call the cube, is 6. Octa, which we talked about earlier, that's 8. Deca, that's 2 and 10. That's our 12. And then the icosahedron is 20.
And as you go through this booklet, they visit those numbers again with they just couldn't do it all on one page. Too much for the kids.
All right, let's look at page 2. And again, in order to, so we may be familiar or with a sphere or unfamiliar, right, depending on familiarity with math. That word is probably a little bit more likely to be familiar. Torus may be a little bit more likely to be unfamiliar. But what are some concrete examples of a sphere and of a torus?
The stacking donuts that little babies play with. In fact, I was in the nursery on Sunday at church and they had those, and this little 11-month-old child is sitting on my back and I was going, it's a red torus, it's a yellow torus.
Pool floaties, that's good. Oranges are spheres, donuts are toruses. I'm reading the chat.
Yeah, I prefer just the edible kind of donut there, Jill. But baby toys are fun too. Right. So there's a great a great way where we can sit with our kids and help them to actually concretely become familiar with these shapes and putting names to it. And as we go back to even with our youngest students, one of the things I remember from our early days of CC, my oldest is now graduated, my youngest is soon to graduate. But I remember from our early days, that one of the big ideas behind classical education was just using words well, right? Going for a walk and naming things accurately. And so this is giving us some language now that we can actually name things accurately, just like Jill did with the 11-month-old, right? Because imagine if that 11-month-old, every time he plays with that, you know, instead of somebody saying, oh, look, it's a donut, they say, oh, look, it's a Taurus. They're naming it appropriately, and they're going to grow up with a head start on their peers.
And they can start
Thanks
a
to Jill.
franchise called Tasty Taurus.
Doesn't sound that good, Lee. Ooh, I don't know.
Well, then you could, well, if you did that, you could think about it as like topologically, and you could do all kinds of shapes that are like equivalent to the torus because they just have one hole. Anyway,
Like a coffee mug is a Taurus.
yes. Well, can you imagine if your coffee mug was made like a donut, but it like somehow was like slowly permeable instead of like just mushing? So you could like literally kind of like an ice cream cone, like have your tea or your coffee and your donut all at once. Okay. All right. And on to lesson on page 3, looking at some applications of solids. And so let's just talk for a minute about this page. What's familiar and unfamiliar on this page?
Well, hopefully what's familiar is all the tops have been naming shapes and some of their parts.
I also like how it relates to the foundation math fact that 3 teaspoons is 2 tablespoons. Is 1 tablespoon, 2 tablespoons is 8 fluid ounce. That's actually a math fact in foundations.
Thanks.
So we have questions about from people that is the foundational math facts going to change anytime soon, or is it something separate?
Now, the foundations does not change. All the foundations math is in the math map, but not the other way around.
Okay. Then we have some nervous moms out there thinking.
So these math facts, right, when we're talking about tablespoons and teaspoons and ounces and cups, what are we measuring?
Volume?
Volume. Could we measure volume in 2D?
No.
No, so volume is when we think about measurements, right? We recognize that each dimension has a unique capacity. So in 1D, we measured length. In 2D, right, we measured area. And so in 3D, now we can measure volume. And we have units that go along with those capacities. And this is a great example of units that go along with volume. Would we ever use these units to measure length?
No,
Would we ever use these units to measure area?
not intentionally.
Right. And so these are strictly volume units, right? And so sometimes helping our kids see how the units match the dimensions helps us to keep track, right, of what it is that we're measuring. And again, it goes back to our tissue box, right? So what kind of units could I use to measure my volume, right? Well, I could use cubic units, right? Which, because I would have 3 dimensions, right? If I was stacking cubes inside, I might have cubic units. But if I only wanted, right, if I wanted area, right, I'm going to have square units. So they're going to be square units. If I just wanted to measure the height of my box, right, then I'm looking at the length. So I'm measuring, right, linear units. So matching our units to our dimensions is one way to help keep track of which units we're looking at. Is there anything else on this page that anybody would like to talk about?
I just want to point out that you cannot do a physics problem if you do not pay attention to your units. So we have a lot of unit problems the whole way throughout the curriculum so that they can actually work on the applications as they become adults.
And I may not have, I don't think I've shared this on any of these calls before, but when I was many years ago now, before I was married, before I was a homeschool teacher, I was teaching in a private school that was building a new building. And it was very excited because I was in the old building that was on a college campus. It was rented space. And we watched the new building being built, and it was beautiful. And we got to move in, and everybody was really excited. Well, after a couple of months, there was a financial crisis because when they did the budgeting, and this was in Florida, so heating and air conditioning was very, very important. They only thought about the square feet, right? The square feet of shape they had in the building versus the cubic feet of capacity. And so they had grossly underestimated the they grossly underestimated what the cost of the air conditioning was going to be. Right. So they basically calculated it based off of like a 1 foot high room throughout instead of 10 foot high. The capacity, the volume of the building was a lot more than the square feet, the area of the building. So just coming back to when Lee talks about, being able to use the appropriate units. And Jill, I see you nodding because your husband does that. And so your husband would have been all over that if they'd hired him. All right. And our last page, speaking of engineering, right? Let's talk for a minute when we talk about our engineering drawings. How hard is it to look at 3D things on a 2D page? And
It's
whether
hard.
that's
It's not so much hard in the sense of you can learn the oils that help you to do that for drawing, but your eye may not focus on the right vertex to see the 3D-ness, even if it's drawn appropriately. So that's another thing that makes it difficult is our eye doesn't know quite always what focus to look at.
I think when you have a lot of people working on the same thing, it has a lot of error possibilities. So Kirsty, when you said about my husband being an engineer, they have to work on plans that all different people have to work on. He's doing structure, someone's doing mechanical, someone else is there, and then the architect is involved. And if one person can't read those plans right, if it's done in 2D, it makes it really difficult, and you wind up with a beam going through a stairway or coming out of a window. So that like you said, doing things 3D into 2D creates a lot of challenges unless you have a lot of people who know what they're doing.
we have to attend really carefully, don't we, to what's there. And just as as Lee was pointing out, right, what do I focus on? So as we look at those cubes in the middle there, one of the ways that we can help to tell our eyes, right, is by using different weights of lines, right? If all of the lines have an equal weight, then we're kind of like, what am I focusing on? But by using some dashed lines, oh, now my brain interprets that as being sort of the back, right? Oh, I can focus on the dark lines. But it's also pretty amazing that when all of us look at this page, right, they are 2D images. All of us can interpret those as being 2D, as being 3D things. So what does that tell us about how God created our brains?
He wants us to see more than we realize.
Right? I mean, he's built us to look beyond, right? And so when we talk about seeing the unseen, when we talk about looking for these patterns that help us to see beyond, right? To see the unseen math, or to see how God, right, the unseen God around us, that he wants us to see more than might be readily apparent, right? Now with AI being trained, right? Because we're telling it how a human brain works, and so it may be a little bit different. But if I was to tell a child, right? If I was to describe these pictures to a child, I'd say, well, they're boxes that have been drawn in 3D, right? I wouldn't say, well, there's a square and then there's a line drawn at this angle and then, right, another line drawn at this angle and another line drawn, right? I wouldn't, now that's how a computer would do it, right? It would break it down into those lines. It wouldn't see it holistically the way we do. And so I just think it's worth, as we're working through these lessons, right, really encouraging ourselves and our students, right, that God has given us this incredible ability to see more than sometimes is just there, and that we should be looking for that, because he promises, right, that when we look for him, that he's going to answer it, and when we seek, we're going to find. I love.
Oh, sorry, Kirsty, I didn't mean to interrupt.
No, go ahead. I was just gonna say, I love the verse in Jeremiah where he says, right, when you ask and you seek, I'm going to show you things you didn't know. And I think this is a kind of an example of that. But go ahead, Jennifer, please.
Yeah, I was just going to say, I think all of that is true and beautiful. And sometimes all of us need more help seeing beyond what we can see, which is why I posted in the chat box that when I was a senior in high school, my calculus teacher not only had the set of platonic shapes, but she informed me one morning when I went in to get help that she bought them for me. And the reason she bought them for me was because I was having trouble picturing them flat on the page, or in a word problem where it wasn't represented on the page at all. And so she said, in order to help you get over this hump, I bought these. And every time you come in and we work on it, we're going to look at these wooden shapes, and I can slide them apart and show you the conic section when I cut it, and I can show you it whole, and this will get you over the hump, and you will eventually be able to picture them. And I thought that was such a grace to me that she was willing to go that extra step. So sometimes it's okay to help our kids too with something physical when they can't extrapolate, see beyond.
That's really good. So we're almost out of time. I want to point something out here that this lesson does, I think, well, is the mapping. So you did day 1 with all your family, and it's week 20, and it's this lesson, and the rest of the week just fell apart for you. Well, look at what you just looked at as family together. You looked at there's only 5 regular polyhedron. You looked at all 5 of them. And there's 2 or 3 main ideas about spheres and polar coordinates, and you looked at those. And then you looked at some of the potential calculations, because volume is that capacity that's related to it. And then here we're doing some artistic drawing. And so if they don't get to do any of that again the rest of the week, you can be confident that finish it off in the summer, pick it up when everybody else is sick and needs an extra workbook, or next year, just go through the map again, and it'll be there again and again and again. So the part of the people keep asking about review. I hope that you can see now that in a single week, you're going to review these 4 big concepts 4 times using very similar ideas, but the shapes and the numbers and the sizes and the layout of the problems will change, just to make them keep thinking.
All right. Well, as Lee mentioned, we are about at 2 o'clock. Are there any last questions that you would like to ask before we jump off? And yeah, I would, just as Jennifer said, I would encourage you all, when you're working with your students or for yourself, to look for the concrete, right? That's how we naturally learn, is by experiencing the concrete and then moving to the abstract. And so anytime we can find some concrete things that we can touch, label, that's going to help us, especially now that we're moving into 3D. because I can't see behind, right? So going back to my tissue box, right? I can't see what's behind my tissue box. Now I can because it's in the mirror. I can see what's here. Right. But if I'm looking at this, I can't see what is behind my tissue box without rotating it and turning it. And so giving your kids the opportunity to do that, to explore the different sides. And that's one of the things that makes 3D hard is I cannot get outside of 3D, right? I can turn this around to see all the different sides, but I can't get a hold of 3D-ness, right? I kind of can with 2D, right? I can picture 2D. I can be outside of 2D and I can sort of see all of it and I could turn it and I could consider it, but I can't get outside of 3D. I'm stuck inside of it. And so that alone makes it a more challenging thing. And so anytime you can give your kids some concrete ways to explore that is going to be really valuable.
And just to add, like we had similar discussion at our house with a different math curriculum before, but then it actually just being foundation, my younger kids can say that, whoa, so God is outside of all this, is outside of 3D. I say, yeah, it's almost like 40, 60, 70, it just blew their mind that how God is beach in time.
All right. Well, thank you, Yachting. That you got a little blurry at the end, but we got the gist of it. So thanks everybody for coming and we'll see you next week. Happy math.